You know, every software problem is really just a case waiting to be solved. There are clues, there are constraints, and if you're smart about it, there's a single correct solution that you can find through pure logic. But what do most of us do? We just start guessing, right? Well, today, we're going to step into the mind of a different kind of programmer, a detective, who actually proves their case before ever writing a single line of code. So let's open the case file.
Here we go. Our investigation starts with case file number 1. Think of this as the reasoning system in action, a framework for getting from a confusing problem statement to a solution that you know is correct. See, every problem leaves behind a trail of evidence, and we're about to follow it.
So, here's our objective. Stated simply, we've got a list of numbers and a target value. The mission? Find two numbers in that list that sum up exactly to the target. Now, it might sound simple, but in our line of work, the approach is everything.
Any good detective will tell you, you never rush the scene. First, you analyze it, you meticulously examine every single piece of evidence. And honestly, this is the most crucial step, because the clues themselves, they're going to tell you exactly what the solution has to be.
The environment we're operating in, we call that the problem space. And what's our input? It's an array of integers, basically just an indexed sequence. Now, that tells us something important. We can move through it one by one, but it also gives us a huge constraint. An array is really slow if you need to look something up. And that single clue, right there, is what's going to motivate our entire strategy.
Now here's the crucial part. It's all about how we frame the problem. Instead of just blindly searching for any old pair of numbers, the detective defines the core relationship that must be true for a solution to even exist. We call this the intent. So for any number we look at, let's call it our candidate, we know exactly what its partner, the complement, has to be to equal that target.
Okay, so to get around that big limitation with the array, that slow lookup, the detective needs a tool, a notebook, if you will. This is the recorder. It's an external memory system, basically a hash map, that stores every candidate we've already seen and its location, or index. And this little trick lets us check for a complement in what we call constant time. It's lightning fast. It's our secret weapon.
Now, what's really fascinating about this framework is that we don't just, pick our tools out of a toolbox. No. The environment and the constraints themselves literally determine what tools are required. We eliminate everything that doesn't fit the evidence, and we're left with only the necessary equipment.
All right, let's start with navigation. How do we move through the data? Well, the problem gives us an indexed sequence, and that kind of implies a single pass is going to be the most efficient. So a linear scan fits perfectly. What about nested loops? Way too slow. That violates our efficiency constraint right out of the gate. Graph or tree traversal? The data doesn't have any relationships or hierarchy, so those are out. See, the evidence points to only one conclusion, a linear scan. Next up, storage. How are we going to manage our notes? We need super fast, constant time lookup to find that complement, right? And we absolutely have to remember the index of each number. So an array by itself, too slow for lookups. A set, it's fast, sure, but it doesn't store the index. A tree, slower than we need. And this right here brilliantly shows why the hash map is our only option. It wasn't chosen, it was derived.
So, with our strategy and tools derived directly from the evidence, we finally arrive at the absolute heart of this method. We are going to solve the entire case on paper, proving our logic is sound before we even think about transcribing it into code.
Okay, let's walk through the proof. Our list is 2, 7, 11, 15, and our target is 9. First, we look at our candidate, 2. The complement we need is 7. So we ask, is 7 in our recorder? Nope. So we note down 2 and its location, and we move on. Next up, we look at candidate 7. The complement we need is 2. So we ask again, is 2 in our recorder? Why, yes, it is. Boom! Case closed. We found the solution with zero guesswork.
And this is the fundamental principle. That table we just filled out, that's our proof. It validates the entire algorithm. If you can't build this proof, it means you don't truly understand the solution, and therefore, you are just not ready to implement it. Period.
Now that the case is basically solved in theory, the final step is really just a formality. Writing the code is no longer an act of discovery or guesswork. It's an act of transcription. We're simply executing a plan that we've already proven is correct.
So let's watch the scanner in action. It picks up the first candidate, 2. It calculates the complement, 7. It checks the recorder, it's empty.
Okay, so it stores 2 and moves on. Then it picks up 7. It calculates the complement, 2. It checks the recorder and finds a match. It returns the indices and the job is done. It's efficient, it's logical, and it was pre-validated.
So, what's the ultimate takeaway from this whole investigation? What's the core principle that this detective operates by, not just for this case, but for every single case? It all comes down to this. The solution is not discovered by fumbling around in the code. It is determined by a rigorous process of deduction before you even open your editor. The complexity, the tools, the correctness, it's all decided up front. The execution just reveals the cost of decisions you've already made. And honestly, that changes everything.